Hello friends, welcome to our channel, Gajpal Learning. In today's video we are going to study about the topic, fractional precipitation, titration curve, and Argentometric titration. So let's start. First is, fractional precipitation. Fractional precipitation is a separation technique used in chemistry to isolate and purify different ions from a solution based on their solubilities. It's particularly useful when dealing with mixtures of ions that have similar chemical properties. Here's a detailed explanation of the process. First, understanding solubility. Fractional precipitation relies on the principle that different ionic compounds have varying solubilities in a given solvent. Some compounds are highly soluble, while others are only sparingly soluble or insoluble in that solvent. Second, selection of precipitating reagent. To perform fractional precipitation, you need to choose a precipitating reagent. This is a chemical that, when added to the solution, will react with one of the ions you want to separate, forming a less soluble compound. Third, formation of precipitates. The chosen precipitating reagent is slowly added to the solution containing the mixture of ions. As it's added, it reacts with one of the ions, forming an insoluble compound or precipitate. The other ions in the solution remain in their ionic form and stay dissolved. Fourth, filtering. After the precipitation reaction has occurred, the mixture is typically left to settle, allowing the precipitate to form solid particles. These solid particles are then separated from the remaining solution using filtration. Fifth, washing and drying. The collected precipitate is often washed with a suitable solvent to remove any impurities or unreacted ions. After washing, it's dried to obtain the pure solid compound. Sixth, repeat if necessary. If there are more ions to separate, you can repeat the process with the remaining solution. This can be done multiple times, each time targeting a specific ion for precipitation. Seventh, collecting and identifying fractions. Throughout the fractional precipitation process, you collect fractions of precipitates, each containing a different ion or group of ions. These fractions can be further analyzed through chemical tests or other techniques to confirm their composition and purity. 8. Applications. Fractional precipitation is widely used in analytical chemistry to separate and identify ions in complex mixtures. It's also used in various industries, including metallurgy for the purification of metals and in wastewater treatment to remove contaminants. Note: one important consideration in fractional precipitation is the choice of reagent and conditions, such as temperature and pH, as they can significantly impact the selectivity and efficiency of the separation. Additionally, careful control and monitoring of the process are essential to achieve the desired degree of separation and purity. Second is titration curve. A titration curve is a graphical representation of the pH, or other relevant property, of a solution being titrated as a function of the volume of the titrant added. It is a crucial tool in analytical chemistry and is used to determine the equivalence point, pKa values, and other important information about a chemical reaction or a solution. Here's a detailed explanation of a titration curve. Key components of a titration curve. X-axis. The x-axis of the curve represents the volume of the titrant added. This is usually measured in milliliters, milliliter, and starts from 0 and goes up to the maximum volume of titrant added. Y-axis. The y-axis represents the property being measured, which can vary depending on the type of titration. The most common property plotted on the y-axis is the pH of the solution. Stages of a typical acid-base titration curve. First, initial pH. At the beginning of the titration, the solution contains only the analyte, the substance being analyzed, and has an initial pH. For example, in an acid-base titration, the analyte might be an acidic solution with a low pH. Second, initial slope. As you start adding the titrant, the substance with a known concentration, the pH of the solution changes gradually. The slope of the curve during this phase is typically gentle, indicating that the solution is not yet near the equivalence point. Third, equivalence point. The equivalence point is the point at which the amount of titrant added is stoichiometrically equivalent to the amount of analyte present. At this point, there's complete neutralization, and the pH undergoes a rapid change. In an acid-base titration, the equivalence point typically occurs at a pH close to 7, neutral, but it can vary depending on the strengths of the acid and base being used. Fourth, post-equivalence point. After passing the equivalence point, the titration curve enters the post-equivalence region. Here, the titrant is in excess, and the pH changes more gradually. The specific shape of this part of the curve depends on the nature of the titration. In the case of a strong acid-strong base titration, the post-equivalence pH is closer to 7. However, in a weak acid-strong base, a weak base-strong acid titration, the post-equivalence pH can be significantly different from 7. Fifth, endpoint. The endpoint is the point where the titration is stopped. It's often determined using an indicator, a pH meter, or other suitable methods. The endpoint might or might not coincide exactly with the equivalence point. Additional considerations. First, buffer regions. In weak acid or weak base titrations, you may observe buffer regions on the titration curve, where the pH changes very slowly. These regions correspond to the presence of a buffer solution, which can resist changes in pH to some extent. Second, pKa values. Titration curves can be used to determine the pKa values of weak acids or bases by analyzing the points of maximum slope on the curve. These points correspond to the half equivalence points. Third, choice of indicator. The choice of indicator in an acid-base titration can significantly affect the appearance of the titration curve and the accuracy of the endpoint determination. In summary, a titration curve is a graphical representation of how the pH, or another property, of a solution changes as a titrant is added. It provides valuable information about the chemical reaction taking place and is a fundamental tool in quantitative analysis and research. Third is Argentometric titration. Argentometric titration is a specialized form of volumetric analysis used in analytical chemistry to determine the concentration of ions that can form insoluble precipitates, typically involving silver ions, Ag+. It is commonly used for the determination of chloride ions, Cl, bromide ions, Br, and iodide ions, I, but can also be used for other anions such as thiocyanate, SCN, and cyanide, Cn. Here's a detailed explanation of argentometric titration. Key concepts and steps in argentometric titration. First, preparation of the sample. The sample containing the analyte, the ion to be determined, is usually in the form of a solution. It needs to be properly prepared and standardized if necessary. Second, addition of silver nitrate, AgNO3, a known volume of a standardized silver nitrate, AgNO3, solution, known as the titrant, is added to the analyte solution. Ag+ ions from the silver nitrate react with the analyte ions to form an insoluble silver salt precipitate. The specific silver salt form depends on the analyte ion, such as AgCl for chloride ions, AgBr for bromide ions, and AgI for iodide ions. Third, precipitation reaction. The precipitation reaction between Ag+ ions and the analyte ions can be represented as follows, using chloride ions as an example. Ag+ plus Cl, to give AgCl down-pointing arrow. The down-pointing arrow symbol indicates the formation of a solid precipitate, AgCl, in the reaction. Fourth, endpoint detection. The endpoint of the titration is determined using a suitable indicator or by monitoring a change in a physical property. Common indicators include potassium chromate, K2CrO4, for chloride ions, which forms a red color upon the formation of silver chromate, and starch for iodide ions, which forms a dark blue-black complex with iodine. The appearance of a specific color or a sudden change in a physical property signals that all analyte ions have reacted with the silver ions, indicating the endpoint. Fifth, calculating concentration. Once the endpoint is reached, you can calculate the concentration of the analyte ion using stoichiometry. The amount of titrant, AgNO3, needed to reach the endpoint is related to the concentration of the analyte ion. Considerations in argentometric titration. First, standardization. It's crucial to standardize the silver nitrate solution before use to ensure its accuracy. This is typically done by titrating it against a known concentration of a chloride solution. Second, choice of indicator. The choice of indicator depends on the specific analyte ion. The indicator should produce a noticeable change in color or property near the endpoint. Third, solubility product, KSP, the solubility product of the precipitate, example, AgCl, AgBr, or AgI, plays a role in the determination of the concentration. It helps in understanding the saturation point of the solution and how much silver ions can be added before precipitation occurs. Argentometric titration is a valuable analytical technique for determining the concentration of ions that form insoluble salts with silver ions. It's widely used in various industries, including environmental testing, pharmaceuticals, and food analysis, where accurate determination of halide ions is essential. Thanks for watching this video. If this was helpful, then please kindly do a subscribe to our channel and hit the bell icon.